So in this lecture we will start our route through the extension of a measure which is defined on a semi-algebra to the measure defined on the sigma-algebra generated by this semi-algebra. We will start with a quite simple lemma which will be useful and used several times. So for that I will need to define what is a continuous measure. So I have a definition. So let's say that we have a class of function C and a class of sets C. So C, remember, it's always a subset of all subsets of omega. So it's a family of subsets of omega, and we have a function mu which is defined on C and which takes values on R plus union plus infinity. And so I will say that, so if I take E, an element of C, I would say that mu, it's continuous from below at E. So here it's from below. So it will be continuous from below at this set E if for all sequence En, so En are sets on C and En increase to E, and by that I mean, so this symbol here will mean two things. First, that the sequence of sets En it's increasing, which means that En it's contained in En plus 1, and that they converge to E in the sense that the union of En greater or equal to 1, it's the set E. So when I write En increase to E, I mean that the sequence En it's increasing and that the union is equal to E. So the requirement is that for any such sequence, mu En converges to mu of E. And note that since we proved that mu it's increasing, this sequence it's in fact increasing and therefore has a limit, and we are requiring the limit to be mu of E. So we will say that mu it's continuous from below because the sequence it's increasing at a set E if this property holds for any sequence En. So let's call that definition 1, and a definition 2 which is very similar. I will take E in C and I will say that mu it's continuous, but now I will say from above at E with a very similar definition if for all sequence En with En in C and En decreasing to C to E, and with a further property. So I will require here also that there exists N0 such that mu of E N0 is finite, and I will comment on this further condition in a second. So if I take any sequence En in C which decreases in E and for which there exists an integer N0 for which mu of En0 is finite, and by this symbol here I mean something very similar now, that the sequence En decreases, which means that En contains En plus 1 and that the intersection of En it's equal to E. So this is the meaning of En decreases to E. So for any such sequence En, we have that mu En, well, converge and since it's a decreasing sequence, it decreases to mu of e. Right? So this is the definition. Continues from below and continues from above. Well, let me comment on this condition. So we require here that there exists a n0, starting from which the sets En, they have all finite measures. And this is very easy to understand. So let's take the line. Let's consider the set En to be, say, the semi-infinite interval at n. Let me represent by L what will be later the measure which we will construct extending the notion of length. So it's clear that we want lambda En to be plus infinity for any n. We have that these sets En decreases to the empty set. So we have here an example in which we have a nice function lambda, which would not be continuous at the empty set if we didn't require lambda En to be finite starting from some n, right? Because, well, lambda of empty, it's 0, so that if we do not require, so let's go back here in the definition, if we do not impose the measure to be finite, we would have here an example of a sequence which decreases to empty and for which lambda En does not converge to lambda of the empty set. So to avoid this situation, we will require that the measure is finite starting from some index. So we may now state our lemma. The lemma states the following. Let's assume that we have an algebra of subsets of omega. So A, it's an algebra. Then let's assume that we have mu, which is defined on A, and take values in R plus union plus infinity. And we will assume that mu is additive. So there are two assumptions here. A, it's an algebra, and mu, it's additive on this algebra. Then my first claim is that, well, assume that mu, it's in fact sigma additive. Then we will prove that mu, it's continuous. At E for all E in A. And by when I'm saying that mu it's continuous at a set E, it means that it's continuous from above and from below. So if mu is sigma additive, we have continuity at any set. Then the second claim is that, well, now assume that mu is continuous from below. And when I'm saying that it's continuous from below without precising which set, at which set it is continuous from below, it means that it's continuous from below at all sets. Then I claim that this implies that mu is sigma additive. And finally, let's assume that mu is continuous from above at the empty set. Here I will require, and I will comment on that later, that mu is finite. So if it's continuous from above, but here we require continuity from above only at the empty set. And if mu is finite, then I claim that mu is again sigma additive. So this is the lemma which will be used several times later and which I will prove now. So proof. I will start assuming that mu is sigma additive. And I want to show that it's continuous from below at some set E in A. Right? So I have E in A, and I consider now a sequence En converging to E, and I want to show that mu of En converges to mu of E, assuming that mu is sigma additive. So let me draw a very simple picture. We have here an increasing sequence, so here is E1, here it's E2, E3, and so on. And to use sigma additivity, I need to transform these sets E1, E2, E3 in sets which are disjoint, and for that I will use the fact that A it's an algebra. So let me define, as you see, it's very easy. Here is a first set, which I will call F1. So F1 will be E1. Then let me call this annulus, which is E2 minus E1 F2. So F2 will be E2 minus E1. And let me proceed in this way by defining Fn to be En minus En minus 1. In this way, these sets Fj are disjoint 2 by 2. Right? Fj intersection Fk, it's empty. First remark, which is clear from the definition of F of the sequence. And then the union of En, which is the set E, right? Because En, it's increasing to E. It's exactly the same as the union of the sets Fk. Well, but now, so E, it's equal to the union, which is a disjoint union of the sets Fk, on the one hand. On the other hand, each of these sets Fk belongs to the algebra, because the sets En belong to the algebra. Right? I didn't write it, but in the definition of continuity, we require the sets En to be in the algebra, and therefore the sets Fn are all in the algebra. So I can use sigma additivity here to say that mu of E is equal to the sum of mu Fk. But this sum, it's equal to the limit as n goes to infinity of the sum from k from 1 to n of mu Fk. And now you see that if I take the union of Fk from 1 to n, I will just get, well, E1 union the second annulus, the third annulus, up to the nth minus 1 annulus. So what I'm saying here is that the union of k from 1 to n of Fk, it's equal to En. Right? By sigma additivity and therefore by additivity of mu, since these sets fk are all disjoint, the sum of the measures it's equal to the measure of the union. And I just proved that the union of fk is equal to mu of n. So this is the limit of mu of en, which proves that mu it's indeed continuous from below at e, right? Because I consider any sequence en increasing to e, and I proved that mu en converges to mu of e. And therefore, mu it's continuous at e, and since this holds for any e, mu it's continuous from below, as we claimed. Now let's prove the second assertion of 1, which is that, so I want to prove that mu it's continuous from above. So I'm assuming that mu it's sigma additive, and I want to show that it's in fact continuous from above. So I'll fix a set E in A. I will consider a sequence En in A, En decreasing to E, and remember, to prove that mu is continuous from above, I have to consider sequence En which are finite, whose measure are finite, so I have to impose the fact that there exists an index n naught such that mu of En naught is finite. And so what I need to show is that for any sequence En satisfying these three conditions, so they belong to the algebra, they decrease to E, and there exists one of these sets which has a finite measure, then I have to prove that mu of En decreases to mu of E. And to prove that, I will use what we already proved, is that mu, which is that mu it's continuous from below. And what's the idea? Well, we have here our sequence of sets. So let's say that we started from E1. Then at some point we reached En0, and this set En0, which is represented here, has finite measure. And then the sequence continues up to the sequence E. So the sequence decreases to the set E. So the idea is to transform this decreasing sequence into an increasing sequence. And how shall we do that? Well, let's take this set, this annulus, as the first set. Then this annulus union the second annulus as a second set, and we will get a sequence which increases to En0 minus E. So let me define that. And we will see in a second why I'm starting from En0 and not from E1. So the first set, let me call it G1. So G1 will be En0 minus the next one, which is En0 plus 1. Then G2. So this is just the set which I represented here. Then the second one will be En0 minus En0 plus 2, and so on, so that Gk will be the set En0 minus En0 plus k. Right? Since the sets En are decreasing, the sequence Gk is increasing. And the sequence of sets Gk increases, well, because this sequence En is decreasing to E, this sequence Gk, it's increasing to En0 minus Ek. All these sets, G1, G2, Gk, belong to the algebra, because by assumption, each of these sets, En, belongs to the algebra, and therefore, by the properties of the algebra, the sequence Gk, it's a sequence of elements of the algebra. So we have a sequence Gk in the algebra, which increases to an element of the algebra. Therefore, since mu it's a sigma-additive, and we proved that any sigma-additive function it's continuous from below, we know from the first part of the proof that mu of Gk increases to mu of En0 minus E. Right? Because I'm sorry here, it's Gk, it's increasing to En0 minus E. So there was a mistake here, I wrote K, but it's E, right? This sequence Gk, it's increasing to this set. So we have that mu of Gk, by the first part of the proof, converge to the measure of En0 minus E. So now, let's just write this here. So we have that mu N0 minus E, it's equal to the limit in K of mu Gk, but mu Gk, it's En0 minus En0 plus K. The measure of En0 is finite. E it's contained in En0. So we've seen that if the measure of E is finite, the measure of this difference is the difference of the measures. So this measure it's in fact mu n E N0 minus mu of E. And this is equal to the limit in K. By the same reasons, since this set has finite measure, this one which is contained in this one has finite measure, and therefore the measure of the difference is the difference of the measures. So this is mu E N0 minus mu of E N0 plus K. So what have we proved? We proved that this difference it's equal to this limit. Since mu of En0 is finite, we can cancel on both sides, and we obtained that the limit of mu En0 plus K it's equal to mu of E, which is what we wanted to prove. So this concludes the proof that mu it's continuous from above at the set E. And since this is general, we have shown that mu is continuous from above. So you see that here that we used at several steps the fact that En0 has finite measure to cancel on each side mu, and to argue that the measure of the difference it's equal to the difference of the measure. This is the reason why we started our construction from En0 and not from E1. Well, let's go to the second statement. It's clear that this first statement will not be used very much, because usually what we will try to prove is that some function is sigma-additive. So we'll start from the continuity to get the sigma-additivity. So this first statement is just for pure knowledge, but it won't be very much useful. The second one and third one instead will be used many times. So here what we want to do is to show that if we have function which is continuous from below, then it's sigma additive. So let's prove that. So this is the second assertion of the lemma. So I'm assuming that mu it's continuous from below. And well, you can imagine the proof. I want to show that mu is sigma additive. So I take a set E, which can be written as a countable union of disjoint sets. So E and EK are all elements of the algebra. And I want to show that mu of E is equal to the sum of mu of EK. Well, we have to use the continuity. So first observation is that if I stop the union at some finite n, this set is contained on E because its union is equal to E. The total union is equal to E. So this inclusion is obvious. We have seen by monotonicity of the measure is that the measure of this set is therefore less or equal than the measure of E. And now let's use the fact that mu is additive to rewrite mu of this union as the sum of the measures so at this step we use the fact that mu is additive. This is true for any n, so we can send n to plus infinity to get that the sum of the measures is less or equal than mu of E. So we have one inequality which always holds, so that the sum of mu of EK it's less or equal than mu of E. And to prove this inequality, we use the fact that mu is additive. Only that. We didn't use any continuity of mu. So what we really need to do is to prove the reversed inequality. And for the reversed inequality, then we will use the fact that EK, that mu is continuous at E. Right? So this is just an observation. Note that this inequality always holds if mu is additive. But now, to prove the identity, let's define Fn to be the union of the first terms. So Fn belongs to the algebra because, well, each of the set Ek belongs to the algebra. Fn, it's an increasing sequence, and it increases to the union of Ek, which is E. Now we know that mu it's continuous from below, so it's continuous from below at E. So we have this increasing sequence. We know that mu of Fn in fact increases to mu of E. And we have already seen that mu of Fn it's equal to the sum of mu of Ek. So this it's equal to Ek. So this is converging to mu of E, which means that mu of E is this limit, and this limit is just the infinite sum. So by using the continuity, we can obtain the equality in this relation instead of the inequality which was following from the additivity. So this proves that if mu is continuous from below, then mu it's indeed sigma additive because we have this identity. So now let's go to the third assertion of the lemma. We will assume that mu is continuous from above at the empty set, that mu is finite, and we want to show that it's sigma additive. So we are assuming that mu is continuous from above at the empty set, and that mu is finite. And we want again to prove that mu is sigma additive. So to prove that mu is sigma additive, let's again consider family of sets E, E, K, which belong to the algebra, and such that E is equal to the joint union of the sets EK, and we want to show that the measure of E is equal to the sum of the measures of EK. Well, so it's clear what we want to do here. We want to construct from this sequence a sequence which decreases to the empty set. So I think you all guess that the correct set is Fn to be equal to k greater or equal than n of Ek. And observe that this set belongs to the algebra A because it is E minus J1, J from 1 to n minus 1 Ej, right? So A, it's an algebra, so it's not closed by countable union, but the set Fn can be written as a finite difference. Therefore, the set Fn belongs to A. So we needed here an argument because, well, this formula does not guarantee that Fn belongs to the algebra A, but that one does. So this is a sequence which is clearly decreasing, and it decreases to the empty set. Fn decreases to the empty set, and since we are assuming that the measure of omega is finite, mu of F1 is finite. Therefore, we have a sequence Fn decreasing of elements of the algebra which are decreasing to the empty set and which have all finite measure. So by the continuity at the empty set, we obtained that mu of Fn is converging to mu of the empty set, which is 0. Well, let's use this fact to prove what we wanted to prove. So mu of E is mu, well, E is the union of all k, so I can write that as union of k equal 1 up to n of Ek, union k greater than n of Ek. By these two sets are sets in the algebra. So by the additivity of mu, this is mu of Ek, k from 1 to n, plus mu of this union, but this union by definition it's Fn plus 1. Now we can pass to the limit in n. This sum will just converge to the sum for k greater or equal to 1 of mu Ek. And this one, we have just seen that it converges to 0. So this expression converges to this sum, and we have proved that mu of E is equal to the sum of mu of Ek, which is exactly what we wanted to show. So this concludes the proof of this lemma. So we have proved this lemma. I just want to make a remark about this condition, that mu is finite, and for that let's recall an example which I introduced. So the example was in the interval 0, 1. We consider the algebra formed by the sets A, B, where A and B are between 0 and 1. And so the algebra is just formed by the union of such finite unions of such sets. And we have defined mu of A, B to be either equal in the case in which A is strictly greater than 0. This is just the length of the interval, B minus A, while if A is equal to 0, we define that as plus infinity. And we have seen that this function mu, it's additive, or you can check that it's additive, but it's not sigma additive. And this we have seen that in the previous lecture, right? We gave an example of a union of sets whose measure is not equal to the measure of the union. So it's not sigma additive, and I leave it to you to check that it's additive. Right? So what I claim is that mu satisfies this assumption. So mu is not finite, of course, we know that it's not finite, but what we are saying here is that it's continuous from above at the empty set. So you take just any sequence decreasing to the empty set, either, so I'll take a sequence En decreasing to the empty set. So each of these sets En belong to the algebra, so they are formed by finite unions of such intervals. Well, either, so let's take the leftmost interval, so En, it's, we can always write En as an1, bn1, union, an, kn, bn, kn, right? So it's an element of the algebra. If it's an element of the algebra generated by the intervals, it can be written in this form. So either an1, and I'm assuming here that anj, it's strictly smaller than anj plus 1, which means that all these intervals are ordered. So this is the leftmost. So I claim that, well, if an1 it's equal to 0 for all n, then the measure of En, it's always plus infinity, and there is nothing to show when we want to prove that mu n converge to mu of 0, because in the proof, in the definition of upper continuity from above, we are requiring that mu of En it's finite for some index n0. But since an1 it's equal to 0 for all n, so this condition is not satisfied, and therefore there is nothing to prove. While if an1 it's so there are two cases, or there exists one an0, 1, which is strictly bigger than 0 for some n0, and then in this case you can show with some work, and we will see that when we will extend to the sigma algebra generated by the intervals, the measure defined on intervals as the length, that indeed it's continuous at this sequence, it's continuous at the empty set. So for that, second, you have to believe me, and we will see in few lectures that this is indeed true. And for that one, well, it's clear. So we have here an example, details will be given later, of a function which is continuous from above at infinity, but which is not sigma additive because it's not finite. So really, we really need this assumption. So now let's start our extension. We have S, a semi-algebra of subsets of some set omega. And we have a function mu, which is defined on S and takes values on R plus union plus infinity. And we would like to extend this function, which is defined on the semi-algebra, to a function defined on the algebra generated by the semi-algebra. So we would like to show that there exists a nu, which is defined on the algebra generated by the semi-algebra, with function which has the same properties as mu. So let's assume here that mu is additive. So we want to prove that there exists a nu which is additive. We want nu to be an extension of mu. This means that, so this is the first property, A. We want nu to be an extension, which means that we want nu of A to be equal to mu of A for any set A in the semi-algebra. So this means that nu is indeed an extension. And we want to prove that, well, this extension is unique. If there are many extensions, well, it's not clear what we mean by when we say that we extend a function. So we want to show that there exists a unique extension, which means that if we have mu1 and mu2 defined on the algebra generated by the semi-algebra, and if mu1 of A is equal to mu2 of A, then for all A in the semi-algebra, then mu1 of E is equal to mu2 of E for any E in the algebra generated by the semi-algebra. So we need to prove these three properties, right? We want to show that given a function on a semi-algebra which is additive, we can always find a function defined on the algebra generated by the semi-algebra, which is an extension, which is additive, and this extension is unique. It's well defined. So this is a theorem we want to prove. So this is the first step in our extension theorem. We will start with a function defined on the semi-algebra, which is additive, and we will use this result to work with a function which is now defined on the algebra generated by the semi-algebra, which is still additive. So this will be the extension, because it's unique, the extension of mu to the algebra generated. So this is the first step in our extension, and this is what I will prove now. Well, in order to to prove this result, we will use the property of the algebra generated by the semi-algebra. And this will turn this proof in a very simple proof. Right? We know that if A belongs to the algebra generated by the semi-algebra, then A can be written as a finite disjoint union of elements of the semi-algebra. And let me insist once more, this is a very special property of the algebra generated by the semi-algebra. This is not true. We won't have any representation of an element of the sigma-algebra generated by a semi-algebra, right? This is a very special property of the algebra generated by a semi-algebra, and this is the property we will use in order to prove this extension. So we want to define nu of A, and we want nu to be additive. Well, if you look at this formula, if you want nu to be additive, it's clear that you want to define nu of A as the sum of nu of Ej. Right? If nu is additive, this identity holds, is in force. But now, each of these sets, it's an element of the semi-algebra. And we want nu to be an extension of mu and mu. So we want nu and mu to be equal on the semi-algebra. Since Ej belongs to the semi-algebra, here we are using the fact that it's an extension, right? So in this identity I'm using the extension, and in this identity I'm using the additivity. So there is no way out, but nu of A should be equal to the sum of mu of Ej whenever A can be written as. So this is the definition we will propose. We will propose to define nu of A as the sum of mu of Ej. Okay, so this is the definition. Now I want to show that with this definition, of course, the first thing we need to prove is that this is well defined, because of course A can have another representation in terms of elements of the semi-algebra. So the first assertion we will prove is that nu is well defined. Then we go back to our claim. We will prove that it's nu with this definition is additive. And finally, we will discuss uniqueness. So let's start with the fact that nu is well defined with this definition. So let me write here that nu of A is equal to the sum from 1 to n of mu of Ej, when A is equal to Ej. So what do we need to show? Is that, well, assume that A can be written as a sum from 1 to m of Fk, where Fk belongs to the semi-algebra. And what we need to prove is that this sum is equal to the sum from 1 to m of mu of Fk. Because we will have here two different definitions for the same object. We need to check that they are equal. So I want to show that this sum is equal to that one. All right. But that's very easy, because we will use here the fact that mu is additive on the semi-algebra. What do I understand by that? Well, let's start with EJ. EJ, it's contained in A, which is equal to the sum or the union from 1 to m of Fk. Which means that EJ, it's equal to EJ intersection k equal to 1 from m Fk, and this is equal the sum from 1 to m of EJ intersection Fk. Now, these two elements are elements of the semi-algebra, which means that EJ intersection Fk, it's also an element of the semi-algebra, and therefore we have here an identity between an element of the semi-algebra and a disjoint union of elements of the semi-algebra. So we can use that mu, it's additive in the semi-algebra. The additivity tells us that mu of EJ, it's equal of the sum of mu of EJ intersection Fk. So I can start from this identity and just replace mu of EJ by the sum of mu of EJ intersection Fk. And this is what I will do here, erasing these identities. So this is, we just proved the sum from 1 to n, sum from k 1 to m of mu EJ intersection Fk. Right? So I'm just replacing mu of EJ by this sum in this expression. And here now we have a symmetric expression in terms of EJ and Fk. So what I am saying is that now I can prove that these two expressions are equal just by repeating here the same argument, replacing E by F and F by E. So that will give me this identity, and therefore these two expressions are equal, which asserts that mu of A is well defined by this formula. So this is the first claim. We just proved that mu is well defined by this formula. So now that we proved that mu is well defined by this formula, so remember that A, it's the sum, the joint union of EJ in the semi-algebra S, and that mu of A is defined by this equation, we want to prove that mu it's additive. Well, it's clear. Well, let's take, so A given by this equation, B given by j equal to 1 up to m f k, and let's assume that A intersection B is the empty set. Right? And we want to prove that mu A union B, it's equal to mu of A plus mu of B. If we prove that it's additive for two sets, we can just iterate this relation and prove finite additivity. Well, if A intersection B it's empty, this means that Fk intersection Ej it's empty for any k and j, which means that A union B, which is the union of this set, it's in fact a disjoint union. So I'll write plus just to remind us that this union, it's empty. This union, it's a union between sets whose intersection is empty. And therefore, since each of these sets belongs to the semi-algebra, I didn't write that Fk belongs to the semi-algebra, but it belongs. Since each of these sets belongs to the semi-algebra, we have here a representation of A union B in terms of a union of the joint sets in the semi-algebra, which means that by definition, nu of A union B, it's equal to the sum of the measures of these sets. So it's equal to the sum from 1 to n of mu ej plus sum k from 1 to m mu of fk. By definition of nu, this first sum is just nu of A. And by definition of B, this second sum, by definition of nu and of B, the second sum is nu of B, and therefore we have that nu of A union B is indeed equal to nu A plus nu B, which is what we wanted to prove. So this shows that nu is indeed additive on the algebra generated by the semi-algebra. So now let's check that nu it's indeed an extension. So that nu of A, it's equal to mu of A if A belongs to the semi-algebra. But this is clear because A can always, since A belongs to the semi-algebra, A can be written as A, and therefore, by definition, by this formula, in which n is equal to 1 and ej is equal to A, we have that nu A is equal to mu of A, which means that nu and mu indeed coincide on the semi-algebra, and therefore that nu is indeed an extension of mu. So the last assertion we have to prove is uniqueness. So uniqueness is as follows. Suppose that we have mu1 and mu2 defined on the algebra generated by the semi-algebra. And suppose that mu1 of A it's equal to mu2 of A for any A in the semi-algebra, and suppose that mu1 and mu2 are additive. Then what we want to show is that mu1 of B is equal to mu2 of B for any B in A. Right, we proved that nu it's additive, so we want to show that there exists a unique extension additive on the algebra. And well, and this is clear. Let's take A, an element, or B, sorry, to conform with this notation, let's take B, an element of the algebra generated by the semi-algebra. Right. Well, B, since it's an element of the algebra generated by the semi-algebra, B can be written as a sum of Ej, of elements of the semi-algebra. Then mu1 of B, since mu1 it's additive, mu1 of B should be equal to the sum of mu1 Ej. but ej it's an element of the semi-algebra, and mu1 and mu2 coincide on the semi-algebra. So I can replace here mu1 by mu2, and use the additivity of mu2 to say that this is mu2 of b, which proves that mu1 of b is equal to mu2 of b, which proves that indeed there exists a unique additive extension of a function defined on the semi-algebra to a function defined on the algebra generated by the semi-algebra. So we just proved this theorem. So we proved that there exists a unique extension to the algebra generated by the semi-algebra of an additive measure. What I want to show now is that if this measure, mu, which is defined on the semi-algebra, is sigma additive, then the extension nu, which we just defined, is also sigma additive. Right? So we define an extension. The extension is unique, so we know what it is. There exists the extension. What I want to show now is that if we started from a sigma additive function, then the extension is also sigma additive. So let's prove that the extension is sigma additive. So we started from mu, and we want to, we are assuming sigma additive on this semi-algebra, and we want to show that nu, which is the extension, is sigma additive in the algebra generated by the semi-algebra. So to prove that, let's assume that A can be written as a countable disjoint union of elements of the algebra. So A and AJ are elements of the algebra generated by the semi-algebra. And we would like to prove that nu of A is equal to the sum of nu of AJ. So this is our goal. Well, so let's use our representation of the elements of the algebra. We know that since A belongs to the algebra, that A can be written as a sum from 1 to n, say, of elements of the semi-algebra. And the same thing can be said about each of these sets A, K. So AK is an element of the algebra, so it can be written as a sum from 1 to say mk of EKL, where each EKL belongs to the semi-algebra. Now, let's recall what is the definition of nu of A. So nu of A, since A is written as the union of EJ, nu of A is the sum from 1 up to n of nu of EJ. Right? So now let's take one of these sets EJ, and let's observe that EJ it's included in A, so that EJ it's equal to EJ intersection A, and A it's given by this union. So let's rewrite that A it's in fact the union of AJ. So let me write it as the union of AK, and each AK can be written as this union. So it's a union of L from 1 up to mk of EKL. So that this is equal to the union of EJ intersection EKL. Right, so we wrote up to this point that EJ is a disjoint union of elements of the semi-algebra. Since each set EJ and EKL belongs to the semi-algebra and the semi-algebra is closed by intersection, we have here expressed an element of the semi-algebra as a countable union, disjoint union of elements of the semi-algebra. And now we can use the fact that mu is sigma additive on the semi-algebra to say that mu of EJ it's equal to the sum of mu EJ intersection EKL. Right? So here we are using in this identity the sigma additivity of mu in the semi-algebra. So we can now replace mu EJ by the sum. And this is what we will do. So we will use this computation to rewrite mu of A as a sum j from 1 up to n, k greater or equal than 1, and then L from 1 up to mk of mu EJ intersection EKL. Now we want to recover from this formula mu of AJ or AK. So AK it's given by this expression, and let me write it here so that mu of AK, right, since AK it's given by this union, by definition of nu of AK, it's equal to the sum from L from 1 up to mk of mu of EKL. Right? So we want to express these, we want to get from this formula the measures nu AK in order to obtain this identity. And so here we'll perform the same argument we did before, just to obtain the set AK from that formula. So what we will do is the following. Let's take the set EKL. EKL, it's contained in AK, which is itself contained in A. So EKL, it's equal to EKL intersection A. And we've seen that the set A, it's equal to the union of the sets EJ. So this is equal to the union from 1 up to n of EKL intersection EJ. And now we can, well, we expressed a set of the semi-algebra in terms of a finite disjoint union of sets in the semi-algebra. So we can use the additivity of mu to say that mu of EKL, it's equal to the sum from j from 1 up to n of mu EKL intersection EJ. Right? So this is just the additivity of mu. Now we can report this identity in that formula. So we can replace the sum in J from 1 to n of mu EJ intersection EKL by mu EKL. So this expression, it's equal to the sum for k greater or equal than 1, L from 1 up to mk of mu EKL. Right? So we just used this identity in this formula. And now, so let me erase the computation we just did in order to obtain this last identity. And now we have just to recall what is nu of AK. So nu of AK, by definition of nu and of AK, it's given by this sum, which is the sum which is appearing here. So this is just nu of AK. And therefore, we have proved that nu of A is equal to the sum for k greater or equal than 1 of mu AK. And this is exactly what we wanted to prove. This is exactly the sigma additivity of nu in the algebra A. And this concludes the proof of the extension of the measure mu, which is defined in the semi-algebra S, and which was assumed to be sigma additive, to a measure nu, which is defined in the algebra generated by the semi-algebra, and which keeps the sigma additivity from mu.